Welcome back to section 2 of chapter 11. In the first section, we were looking at making histograms, dot plots, and box plots. In this section, we're going to be using those plots to start comparing data sets. That's one of the big reasons why we graph things, is so we get the visual so we can use it to compare. So, our learning targets for today: I can use measure of center and spread to compare data sets. We're going to be looking at what some of these measures of center are and what some measures of spread are. So starting out using dot plots, Sawyer has narrowed his car search down to 2 different types of cars. To make an informed decision, he gathers data on an estimated highway fuel efficiency, miles per gallon, of the 2 different types of cars. The dot plots show the data for each type. And remember, with dot plots, we actually see the data. So for type 1, we have 2 that are 33. We have 3 that have 34 miles a gallon, 3 that have 35 miles a gallon. So we can actually write out the data, and we will be doing that here in just a moment. But first, the question: if highway fuel efficiency is the most important feature for Sawyer, which type of car should he purchase? Well, all we have to do for this is look at the graph. Oh, what color? I'll go with blue. Look at the graph. In type 1, we see most of the data is clustered down here between 32 and 38 miles a gallon. In type 2, most of the data is between 35 and 44 miles per gallon, which tells us that type 2 has a higher fuel efficiency, higher miles per gallon. If that's what he was going for, I would go for that one. Now, in each of them, we have these guys way out here. Those are called outliers. And those will affect the mean a little bit. They'll also affect our spread or variability a bit as well. It's nice that we had those outliers. I'd love to always hit that 51 miles per gallon in the car, but it doesn't look like that is a common thing. So looking at these, like Sawyer should purchase the Type 2. It's higher. Now it's more spread out. It has more variability, so it's not quite as reliable, but even at the low end, it's still as good or better than most of the Type 1 cars. So what if we want more information about this? We want to get better statistics. We want numbers to help with our argument. Numbers are good to help with arguments. Which one's bigger? Which one's smaller? It's like, oh, this one's bigger. All right, how much? So we have a couple things. We learned about the median already, and we'll see that again when we get to the box plots. But right now, we're going to calculate the mean. Now, the mean is what we generally think of when we think of average. It's the measure of center like all the rest. It's where we just add them all up and divide by the total number. So if we were going to find the mean of type 1, we're going to add up the different numbers. So we have a couple 33s plus a couple 34s. Let's see, 3 of those, 3 35s, plus another 3 36s, plus 2 37s, plus 2 30, well, that's not a 3 at all, 2 38s, plus the 41, and we're going to take all of those and we're going to divide by how many did we have? We had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we had 16 different data points, So we're going to add all those up and divide by 16. Could we add them all up in our heads? Yes, we probably could. Don't add them all up in your head. Use a calculator. We've got 16 numbers. There's no reason to do that. So we're going to add that up. Let's see. 33 plus 33 plus 34. 35.75 miles per gallon for type 1. You can do the same thing with type 2. If you are uncomfortable finding the mean, or you're not sure and you want to practice, pause this. Add the type 2 up. Divide by the total number there. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's 16 again. When you do that, you should get that the type 2 mean is 40.25 miles per gallon. So we can use those means. Say type 2 has 4.5 miles per gallon more on average than the type 1 car. That can help us. Then we can also find the MAD, the mean absolute deviation. So to find that, to find the MAD, we're going to take each of our values, subtract the mean. So it's going to be the value minus the mean. So the first one, we're going to have 33 minus the mean, 35.75. And then we'll have the next one, 33 minus the mean, 35.75. Then the next one, 34 minus the mean, 35.75. Another 34 minus 35.75. And then another 34 minus 35.75. Then a 35 minus 35.75. Another 35 minus 35.75. Could you see how this could be a little bit time consuming to do this? I'm going to show you how to do this not by hand. But it's important to see what we're doing. So, but we're going to do all of these all the way up, all the way down to 41 minus 35.75. And then what we'll find is when we do those subtractions, everything below the mean is going to be negative. Everything above the mean is going to be positive. If we add them together, we will get 0. That doesn't help us. So to avoid getting 0 for this mean absolute deviation, we're going to find the absolute value of all of these. So they become positive. We find all the absolute values, so they're positive. Then after that, we're going to find the mean of those absolute values. That's why it's called the mean absolute deviation. All these numbers are the deviations. Find the absolute values, and then we're finding the mean of those. So with 16 data points, that could take a little while. We could shorten it because the 33 minus 35.75 is going to be the same both times. So we could do it once times 2. We could do the 34 minus 35.75 times 3. We could do the 35 minus 35.75 times 3 because we have 3 of them. So that could help us out a little bit. But it still can be a little bit time consuming. So how can we help this out? Well, for that, we're going to turn to our friendly calculator, Desmos. So if you go to desmos.com, just open up the graphing calculator. Pulls this up. We're really not going to use this part of it right now. We're only going to use the calculation part. The very first thing we need to do is we need to tell Desmos what it is that we're doing. So we're going to enter our lists. To do that, we're going to name it. I'm going to name mine D. And then it's going to equal, and then we use the square brackets. That's going to let us put in a list. Type in the numbers separated by commas. So as we type in all these numbers, we're going to use this. Now our list is going to be called D. So we're going to go down to the next line here in just a second. I just typed in all of those numbers. Go down to the next line, and we're going to find the mean. So we're just going to type mean, and then parentheses, D. We're going to find the mean of D. Oh, look, there's that 35.75. We could type stats of D. We have our 5-number summary here, right there. We could type MAD of D. That's our mean absolute deviation, 1.625. And then the other deviation we'll learn later on this chapter is the standard deviation. ST dev, standard deviation of D, is 2.1134. Now that does essentially the same thing as the MAD. It does it in a slightly different way, but we're still looking at that. What the mean average absolute deviation is it is the average distance from the mean of the points. So in our case, the MAD was 1.625 for type 1, which means that on average, the cars are about 1.625 miles per gallon away from the mean. So if you want to do this for type 2, if you wanted to try it out, type it into the list exactly like that. Remember, square brackets. And then the mean should come out to be 40.25. And the MAD should come out to be 2.94. So you can check your answers on that. Just type it into it. What's fun is if we have a bunch of problems that are the same, we could have all this stuff done, then we could just change the numbers in the list and it'll change it for us. If we want to see, hey, what would happen if I took out that outlier at 41? I'd go up, delete the 41, and all my numbers will change going down here. So Desmos makes it really easy to play around with data to see what's going on. All right, what if we're going to use box plots? Let's grab some box plots. Caitlin and Philip go to a neighboring high school. Go to neighboring high schools, and both are sponsoring charity fundraisers. Caitlin claims that students at her school are raising more for charity than the students at Philip's school. So the amounts raised in a random sample of 30 students at each school are shown in the dot plots. Do the data support Caitlin's claim? Well, looking at it, at Philip's school, we have the first quartile here is pretty much in line with the median at Caitlin's school, which means that the top 50%, so the top 15 people of the sample, are selling what the top 75% at Philip's school is selling. So to me, this is looking like Philip's school is doing better. The median is higher than the median. We have 75% of students are in the top 50%. They do both have the same minimum and maximum, but we're able to see what the box is doing. In Philip's school, we have only a few people that are below that $45 range. Everyone else is above. Whereas at Caitlin's school, 50% are below and 50% are above, at least of the sample. And so that's just by looking at the box plot. We could look at the numbers. From the box plot, it's pretty easy to get that 5-number summary. So we have Caitlin's high school, Philip's high school. our minimums, maximums, those are the same, and then our quartiles, medians, third quartiles. Notice that, again, like we saw, Philip's first quartile is where Caitlin's median is, which means that we have way more people selling as good or better than half the people in Caitlin's school. We have the interquartile range here as well. The interquartile range is the distance in the box. The interquartile range is quite literally Q3 minus Q1. 52 minus 32 was 20. 56 minus 45 was 11. So that means the middle 50% of people are spread out over 20 for Caitlin's school, and they're only spread out over 11 for Phillips's school. So going from box plots, we can compare the box plots as a plot, and we can also take it into our 5-number summary and look at the actual values as well. If we were given data to compare, making a 5-number summary, then box plots like this, where they're stacked on top of each other, is a great way of comparing data. Now, what if we were going to use histograms? So a marketing team compares the ages of random sample of 30 viewers of 2 popular new shows to decide which product to advertise during each show. During which show should the marketing team advertise a product that is targeted at adults ages 20 to 29? So first of all, notice that our scales are about the same. Here in the first show, we're going from 25 to 44, and it's really lumped. The second show is spread out a lot more, but its age ranges go from 15 all the way up to 54, but it's very spread out. So if we're looking for 20 to 29, well, we have 8 in the 25 to 29. Here we have 5 in the 25 to 29, but we also have 3 in the younger one. So here there are actually 8 people out of the sample for each of them. So what else could we do? We could look at the spread. So we have 8 people out of the sample, but we also have the ones right on the other side of it. Hey, it's designed for someone in their 20s. Does that mean someone who's 19 wouldn't also enjoy it, or someone who's 30, 31? They may enjoy it too. Here, this is kind of the cutoff. So here I would be in show 1. I'd be designing stuff more for those slightly older audiences. Whereas show 2, I would pick stuff that's designed for a wide range of audiences. And also from here, we can see that the center of show 1 is higher than the center of show 2. And the spread of show 1 is a lot less than the spread of show 2. So to review, we can look at the different plots, and different plots show us different things. Remember that dot plots show us the actual data points, so we can see the data, we can see if there's gaps in the data, we can see outliers, we can see peaks, and then we can also find means, and we can find that mean absolute deviation. Box plots are great for showing the minimums, maximums, the median, the quartile, kind of shows that spread, so we can compare those pieces. Remember that we can't see the actual data from a box plot or a histogram like we can from a dot plot. And then histograms allow us to compare ranges a lot better. The box plots don't allow us to compare ranges quite like that. So this is an overview of how we can compare data sets using our graphs and using some numbers, either our mean and mean absolute deviation or the 5-number summary. So with that, I'll leave you to it. Remember, to keep working problems, keep asking questions, and as always, happy mathing.